Hi, my name is Daniel Monforti. I'm an application engineer with Rigol Technologies, and today I'll be showing how our new software S1220 can be used to capture ASK and FSK signals and then emulate those signals for debugging purposes. S1220 is designed to work in conjunction with one of our 3.2 GHz or 7.5 GHz spectrum analyzers. For this video, I'm using our DSA 875 spectrum analyzer in conjunction with S1220 to capture the modulated signal. In order to demonstrate S1220, I've connected an Iris hub with a GE outdoor switch that's going to use Z-Wave communication to send information to toggle this light switch over here. Z-Wave operates at the 908 megahertz range, and on S1220 I'm able to capture the actual signal being sent in the packets. So I'm going to turn on the light like this, and then I can also turn it off. And then with Z-Wave technology and with S1220 we can actually capture the packets getting sent, and right here in the waveform itself we can see the information. In order to capture the Z-Wave signal that's being sent from the Iris hub to the outdoor switch, I'm going to first be using S1220, and then with this software I'm going to go in and zero in on the information that's being sent. So let's first start off with looking more at the waveform itself. And as you can see, it's a rather noisy signal, and we can certainly pare down some of the information that we're capturing, because it looks like the intro sort of information and the last sort of information are rather just oscillating zeros and ones and just padding the sort of signal. So I'm first going to turn on a trigger delay, and I'm going to go with about 2 milliseconds. And then with this, we're going to see the signal get shifted over, and here's the rather important data that we want to zero in on. So next I'm actually going to expand the waveform, and I'm going to change the scale to end at, let's say, right around, let's go with 28. Seems to work. So this is the signal that we're interested in right here. This is the actual information that's being transmitted from the two devices. So with this, we can see, based off this scale, it starts at around 28 to 30 or so of information. So with the decode, we can actually go up and see that right around, once it lines up, right around here is where the actual information starts. And then it's going to stop again right around 250. So somewhere right around in, actually here-ish. So our important information is here. So just to zoom in a little bit more, we can actually change the scaling for the information so that instead of being 512 bytes, we'll actually drop it down to, let's go with 280 bits coming in. And then this will also change the scale on your waveform. And with the eye diagram, you can also see it's a rather noisy signal, and we're still getting the carrier power along with deviation along with our signal decode. Another important piece of information is Z-Wave is actually using Manchester encoding. So this is actually the way the signal is looking for the device when it's decoded. Next, I will be duplicating the signal by first creating an ARB with the data captured. I'll be using our DG1062Z waveform generator to create the digital signal, and then to modulate the signal I'll be using our DSG830 RF source. So here is actually the captured waveform that I generated with our DG1062Z and the DG830. So first we can go in and we can actually set some scaling and set some times. So I'm going to go through based off this sort of image. I'm going to set the time to delay it out. Let's go with 2 milliseconds. Let's turn that on. And then let's see how it's shifted over here in the time. Next, I'm going to actually double click on the image, and you can make it larger, and I can actually change the scaling out over here. And let's drop this down to 30. And this will shorten up the image so we can see a lot more clear information of the data. So for the signal that we captured, it starts out with a whole bunch of zeros and ones just padding the front of the signal and the back of the signal. And then here's the actual data in between. We can go through and we can change all the scaling like before. And then this will also show us the important information for the carrier power, the deviation, and carrier frequency. And then down in here we can actually see the modulated signal. So based on the waveform over here, it starts around bit 30 is when we start actually seeing the data. So right around here is when the actual information starts with this 0 pad, and then the information is just demodulated all through here. Since ZWave is a Manchester encoded signal, I can also turn on Manchester encoding just so we can see the actual captured data with correct format. And it's starting right around here as well once again. And then here's the actual signal being captured, and it goes all the way out to here is where it starts, and then it goes back to the 0 pad. So with our sort of software, you can do some debugging sort of techniques, along with basically go through and make certain that the signal that you're transmitting is the correct one that you're supposed to be. For the actual emulation, we're pretty much using it just to debug the signal and look at the signal, along with we can use it for seeing, basically working on any testing for multiple devices, along with doing some RF testing, some antenna testing for the product without actually having a working prototype, along with some environmental testing and some noise, basically generating a whole bunch of noise at your given frequency. These two images show the captured signal from the home automation system along with the generated signal. This can help with enclosure, RF, and new product environmental testing, allowing for reduction of noise along with determination of problems with RF communication along with network integrity. S1220 is an excellent software package that is designed to improve the capabilities of our 3.2 GHz and 7.5 GHz spectrum analyzer. It will assist in identifying timing, modulation, power, and data errors that could be occurring in an ASK or FSK RF signal. S1220 adds all these capabilities to your spectrum analyzer for around $400. If you have any questions regarding this product or the products seen in this video, please contact us at Rigol or visit rigolna.com for more details.